Hello, I'm Jason. Welcome to the Laplace Transform Tutor. And here what we're going to do in this lesson and in this whole set of lessons is really build your skills so that you can master how to use the Laplace transform. Now, I expect you to know absolutely nothing about the Laplace transform going into this course, but at the end of it, you'll not only know what the transform is, but also how to use it and how to use a table of Laplace transforms and also the Laplace transform properties to take Laplace transforms and also inverse Laplace transforms. So it's a very practical skill that we use in science and engineering classes in order to really solve some more complicated problems. And you'll find that lots and lots of different classes that you'll take as you go on in your engineering sequence or in your science sequence will use the Laplace transform. So if you ever get to a class in electrical engineering or mechanics or pure mathematics or differential equations where Laplace transforms are used, then what you'll be able to do is come into here and get that whole sequence of information on how to use this very powerful tool along with lots of problems to practice your skills. So I'm going to obviously write some math on the board in a second, but in the general scheme of things, what the heck is this thing called a Laplace transform? Well, first of all, it is calculus, so you have to know some calculus in order to be able to calculate the transform. So I expect you up until this point to know a little bit of calculus, really not much more than calculus 1, to be honest with you, will enable you to be able to do the math here. But you will have to be proficient with it. Also, obviously, your algebra skills, because I know that you all know how to do basic algebra, but when you get into taking some of these transforms, it can quickly explode into a bunch of things to simplify. None of it's hard, it's just a lot of little terms to keep track of, and so we'll be doing that here, and I'll show you as I go. But it's basically calculus, and what you're basically doing is you're using a technique to take a function. So here we're going to be talking about functions of time, but really it's any function. You know, f of x you normally study in algebra, but you know, when you get into engineering and studying real systems, you're usually talking about functions of time, things that change with time. For instance, in electrical engineering, you might have an input signal, you know, like a sine, wave, or some kind of random voice, recording of a voice might give you an amplitude as a function of time. That would be a function of time, right? And so the Laplace transform takes a function of time and transforms it to a new function that's in a new way of representing that original function. And you might say, well, why would you ever care about doing that? And the truth is, the reason why it works is beyond the scope of what I'm talking about right now. But basically, Laplace transforms lets you solve a lot of different types of differential equations in an easier way than doing them by hand. So in the original way. So if you think back to my differential equations tutor or any class that you may have taken in differential equations, you should agree with me that it's kind of a nightmare to solve a lot of differential equations. There's a lot of math involved, a lot of theory, and differential equations really have a lot of different techniques. So you may do method of undetermined coefficients in differential equations. You might do integrating factors in differential equations. You might use exact differential equations. There's lots of different ways to solve differential equations, and a lot of it boils down to recognizing what the equation is, figuring out the method that works, and then applying it. And so it seems to be disconnected, though, because there's lots of different techniques for different styles of differential equations. Laplace transform is a unified method that really allows you to take a differential equation and apply the transform to it and change it into a new form that's easier to solve. And then when you get the answer in the Laplace domain, or the S domain we'll talk about in a minute, then you can transform the answer back into the time domain. That's why it's called a transform. We take the problem, or the function, or whatever it is, we transform it into the Laplace domain, which we're going to call the S domain. And a lot of times, doing the solution in that domain, it just becomes algebra or some other easier, simple solution method than differential equations, brute force method. So we solve it over here in the Laplace domain, or the S domain. We get an answer, and then we can take that and inverse transform it back into a function of time. So that's kind of, without getting into the details, that's basically why it's useful. And as you know, differential equations are used in all branches of science and engineering. We use them in electric circuits, we use them in mechanical systems, use them in control systems theory, use them in chemical engineering, aerospace engineering. Differential equations are everywhere, and because of that, and because Laplace transform is kind of a general method, to make these types of problems easier, you're going to find that Laplace transforms pop up in all kinds of different situations. And so that's why I want to put this tutorial in its own little course, because you can use it if you're a mechanical engineer, electrical engineer, physicist, anything. So let's just dive into it first of all and talk about it a little bit. So we have what we call the Laplace transform. Okay? And I'm not going to beat around the bush too much. We're just going to write it on the board and we'll talk about it. So the Laplace transform gives you a function in the Laplace domain, which is the S domain. That's why you're getting a function, capital F of S. That's what you're arriving at when you perform this thing called the Laplace transform. And it's the integral from 0 up to infinity of e to the minus st times f of t dt. So this, ladies and gentlemen, is the famous Laplace transform. All right? So what you're doing, all right, is if I give you a function of time, think about any function of time. Could be a square wave, could be a sine of t, could be a sawtooth, could be any function of time you want. Could be x squared or some function of time squared. You stick that function of time in f of t. And then you multiply by this exponential e to the minus st, right? And so you're getting something inside of the integral sign. You integrate it over time, right? And then you apply the limits of integration to the answer that you get, which are obviously going into your time spots because you're integrating over time. So the limits of integration is from 0 to infinity in terms of time, right? Then when you do all of that, you're going to get just a function of s back. Because if you integrate over time and then you plug in limits of integration over time, there's no t anymore left in what you've done. There's just the other aspects of it here. So there's no t anymore here, there's no t anymore here because you've plugged in limits of integration. Only s remains. So when you do a Laplace transform properly, you get purely a function of s. And so that's the notation here. You put f of t, little f of t is your input function. And out of this computation comes another function. We call it capital F. We use the same letter, capital F and little f, to imply that little f and capital F are related to one another. We put a little f into the Laplace transform, and we get a capital F out, which is a function of s. All right? So we can also write as the following. Capital F of S, which is the Laplace transform, is curly L, I don't know how else you would say that, right? F of t. So this is the shorthand way of saying, hey, I'm going to take the Laplace transform of some function of time, or some function, and when I do that, I'm just going to get a pure function of s. So these two things are exactly the same thing. This is the shorthand way of writing what you're doing. You're taking the Laplace transform of a function of time. This is kind of the details. This is what you actually do. You have to multiply this, you have to integrate it, you have to plug in the limits of integration. So what we're doing is we're transforming a function from the time domain to the s domain. That's why I'm telling you that, because the answers that you get are just functions of what we call s. And so we get a new function as a result of that. And so I know that you've seen this kind of action before where you have 0 and infinity up on an integral. You probably saw that in calculus, but just to refresh your memory, that's called an improper integral, right? So when you have an improper integral, I know you've studied this once probably a long time ago, but basically when you have any kind of 0 to infinity e to the minus st f of t dt, what you really are doing is you do the integration, but what you do is you take the limit. So what I'm going to do is I'll say, let me write it in a different color. What you're really doing here is you're taking the limit. And you'll see what I mean in a minute. As h goes to infinity of the integral from 0 to h e to the minus st f of t dt. I'm just mostly explaining what you're doing with the calculus. When you see an integral like this with one of the limits of integration is an infinity, then what you're really doing is you're taking the integral and you pretend that this top number is just some variable. You calculate the integral and then you take the limit as h goes to infinity. That's how you would write it mathematically. But in practice, what you really do is you evaluate the integral, you plug infinity in one limit and 0 in the other limit, and then you know how to evaluate infinities. You know, if they're on the denominator, if they're on the numerator, they might drive your answer a different way. And so that's basically what you're doing. But mathematically, rigorously, what you're doing is you're integrating the guy, and then you're taking the limit as this limit goes to infinity. All right, so what I would like to do at this point is calculate a Laplace transform. Basically what you have is, we have the definition that was on the board a minute ago. That's really the bread and butter of it. If you understood how to apply that to all situations, then you wouldn't need me. You would just do the Laplace transform all the time. But the truth is that as you do some of these things, there's a little bit of tricks along the way to help make it comprehensible to you, and I'm going to show you those here. And what you're going to find pretty quickly in any book that deals with the Laplace transform is they're going to give you a table of transforms. In other words, there are some pretty basic functions that are pretty easy to apply this definition to, that you get the answer, and that answer is very useful going forward. Because some functions pop up in nature all the time. You know, exponentials pop up all the time. For instance. So we want to learn how to take the Laplace transform of things like exponentials and things like cosines and sines, because those things pop up all the time. So what we're going to do in this lesson, in the next few lessons, is we're going to apply that definition of the Laplace transform, this full-blown definition of the Laplace transform, to a few core functions. And then we're going to assemble our own table of Laplace transforms, which in many cases you'll just find them listed in a book, but I'm going to derive how we get there so that you'll understand how we're applying this. Once you have a basic table of Laplace transforms of common functions, then what you typically do is you use that table to explore more complicated functions. So we're kind of getting our footing. We first learn what the real definition of Laplace transform is, then we're going to apply it to some simple functions. We're going to assemble our table of common functions that are useful to know the Laplace transform, and then we'll apply that to many problems going forward. So the most important function that you could probably know how to, or want to know how to take the Laplace transform of, would be the Laplace transform of the function e to the lambda t. E to the lambda t. Now, this is just an exponential. It's e to the t. It's a function of time, right? But there's a constant in front. We're calling it lambda. In your book, it might say e to the at, or it might say e to the bt, or it might say e to the alpha t, e to the beta t. It doesn't matter. But there is some number in front of t. It could be 1, it could be 2. It's left open-ended because a lot of times exponentials pop up in solutions to differential equations. They pop up in lots of physical systems, right? So it's an exponential if it's e to the t. The actual value of lambda just changes the slight shape of what it looks like. So we're leaving that as a constant left open in there, but we want to find out in general what would this Laplace transform be. So the way you do it is you just apply it directly, 0 to infinity, and you apply that Laplace transform, which if you remember was e to the minus st f of t dt. This was the general equation for the Laplace transform. So then what we do is we say 0 to infinity, e to the minus st, then we put our function of time in here, which is e to the lambda t dt. And this is what we want to integrate. And we suspect and we claim, and I'm telling you that once you do this properly, all you get is a function of s. And we say that that Laplace transform function of s is inexorably tied to the function of time through this thing called the transform. And you have to trust me on faith that once you know how to do these transforms, and once you get proficient at them, that they help you solve real problems. You're going to have to take that part on faith. We're going to get to that part a little bit later. All right? So what we're going to do is begin to evaluate this integral. I could just give you the answer. Of course I could do that, but I want to walk you through it so that you can really feel like you understand what's really going on. So notice this is 2 exponentials. So we can simply combine the exponents at the top. That's something we can do because these exponentials are multiplied together, right? So we can say that we'll have negative s minus lambda dt. Make sure you agree that there's nothing different here. If you distribute the negative in, you get negative s, which is what we have here. And we have a t here as well, right? Negative st, and then here this will be positive lambda t. So basically, we are adding these guys together in the exponent. We're basically adding negative st plus lambda t. We're adding that together, but I pull the negative sign out. So, but it still becomes negative st plus lambda t in the exponential there. All right, so what you need to do is integrate this, right? Integrate this. This is an exponential. Integrals of exponentials are relatively simple. The only thing is, notice, we're integrating over time. Here is your time variable. Lambda is just a constant. S is going to end up being a variable that we are going to have in our transform in the end. But since we're not integrating over S, we're integrating over t, you basically treat S as a constant. And that's really important for you to understand. You know, anytime you take derivatives or integrals, you have to look at what variable you're taking it with respect to. If I give you an expression, I say take derivative with respect to x, if you're talking about derivatives, then you pretend everything else besides x is a constant in that function. That's how you take partial derivatives, right? Well, in integrals, it's the same thing. If we're integrating over time, then this is the variable we care about. Every other letter or symbol in there, you pretend is a constant. So for the purposes of this integral, you pretend that s is a constant and lambda is also a constant, which means that everything in front of the t is really just a constant. So it's like a giant number here. So this integral looks intimidating, but really since it's all just a constant, it's not that intimidating. So many of you can look at this and write the answer to the integral down, but a lot of times we have to make a substitution to make it absolutely clear. And so what you would do is you would say u is equal to minus s minus lambda, right, t. So we want to make a substitution because we want to make it an easy integral to solve. So when I do this off to the side, I'm doing a substitution. I say du dt is equal to, now notice if I'm taking a derivative with respect to time, this whole thing is a constant. So the derivative is just going to be minus s minus lambda, because it's almost like this is just the number 3 or the number 5 or the number 7 out in front of the time. The t just disappears for a first derivative. Now since we're going to end up substituting it back here, we want to solve for dt. And so what we're going to get is negative 1 over s minus lambda du. All we've done here is move the dt over here, and then we've taken all of this stuff and moved it over here so we could solve for dt, getting 1 over s minus lambda du. All right, so now that we have that, we want to take this and stick it back in and substitute into our integral, so we'll change colors again. And for now, we're going to leave the limits of integration 0 to infinity. We're not going to change them right now because we're going to, we'll see how to handle that in a minute. It becomes e to the power of u, because this is exactly coming from that. And dt just becomes what we have found here. So it's going to be negative 1 over s minus lambda du. Right? So that substitution just goes in. Now remember, this is an integral over du now, right? So everything in here is, again, just a constant. It's just a constant. So what we're going to have here, we pull the whole thing out, negative 1 over s minus lambda comes out. We integrate from 0 to infinity, e to the u du. Now we did this whole thing so that we could get an integral into a form that we know how to solve very easily, right? And so what we're going to do then is say we have negative 1 over s minus lambda. The integral of e to the u still remains e to the u. And again, I'm leaving my limits of integration 0 to infinity for now, because what I'm going to do before I apply the limits of integration is I'm going to substitute back in for u. So what I'm going to have is negative 1 over s minus lambda, and then u is going to come right back substituted in as it was before, e to the minus s minus lambda t. Now it goes from 0 to infinity. So you see, I realize that as you have the limits of integration here, this really, if this were a true statement, you would have to transform the limits of integration into limits of u. And this would have to be limits of u. But I'm not going to substitute the limits in until after I've plugged in for u. So I end up having a function of time. Here's a limits in terms of t. And so then I can substitute everything in as exactly as I want to. And then what I'm going to get is negative 1 over s minus lambda, right? And then we have to apply this in. So what this basically becomes, if you think about it, this is negative s minus lambda times t, and I'm putting infinity in for t. So really it becomes e to the negative infinity. It doesn't matter what s and t are. If I put infinity here, it's going to be negative infinity. And then you do a subtraction because you're evaluating the limits, e to the 0 because 0 goes in there. Now this becomes very tractable because we know that e to the negative infinity, it's like taking that limit. What you're going to have, e to the negative infinity, is like 1 over e to the infinity. So what you're going to have, this guy is going to be 0, and this guy, anything to the power of 0, is just a 1. So you have a negative 1 here. And this whole thing evaluates to negative 1, which makes a positive 1 when you multiply this whole thing here. So you get 1 over s minus lambda. 1 over s minus lambda. All right, and so what I'm going to do then is show you that through this whole situation, all we did was we found the Laplace transform of this guy and said that it was equal to that. So let me go to the next board and summarize that because it's a very important result. So what we found is that the Laplace transform of e to the lambda times t, which is just e to the power of some number times t, is just equal to 1 over s minus lambda. So, for instance, if it was e to the 2t, then it would be 1 over s minus 2. If it were e to the 7t, it would be 1 over s minus 7. If it were e to the 4t, it would be 1 over s minus 4. So you see what we get as a result is just a function of s. Lambda is just a constant. It's going to be locked down by whatever we start with, right? So the answer that we get, f of s, capital F of s, remember we said, let me go back. We said that when you do this Laplace transform, you should get just a function of s, and that's what we call it, capital F of s. And that's exactly what we got. We got a single function, pretty simple looking function, just a function of s. This guy is just a constant there. Now, since it's in the denominator, and we don't want any zeros to be in our denominator because then you get undefined, parts of the Laplace transform or infinity parts, then what you can also say is that this is valid for s greater than lambda. That just ensures that the denominator is not going to be 0 and ensures the denominator is going to be positive. This is something that mathematically you write down just to lock it down. You don't have any zeros in the bottom, but realistically you don't really use this fact all that terribly much when you're solving essential basic problems with a Laplace transform. Now this is an important result, and it's important enough that I'm going to circle it for you, right? I'll circle the whole thing, in fact. And it's also important enough that we want to draw your attention to something else. Let me change to blue here. In the special case, let's say lambda is equal to 0. So let's say that lambda is just equal to 0. Then you would have e to the 0 times t, right? Which would be e to the 0. That would be my function of time. If lambda were 0, it would be e to the 0t. And e to the 0 is just 1, because anything to the power of 0 is just 1. So because of this, we can draw kind of another conclusion that's already here, but we can kind of write it ourselves. We can say that the Laplace transform of the number 1, right, would be 1 over s minus 0, right? Because the way you would come up with that is you would say, which would be 1 over s. Right? The way you would come up with that is you would say, all right, I can take the special case when lambda is 0. In that case, this exponential just becomes a 1, so it's the same as taking the Laplace transform of 1, and then we'd be putting lambda equals 0 in here, getting an answer of 1 over s. So the Laplace transform of the number 1 is just 1 over s. And that's important enough. Well, I will also circle it. And of course, it's for s greater than 0, because you don't want any denominator driving the whole thing to infinity. So this is the first important conclusion of what we have done here. I'll go quickly through a brief history of what we've done. We basically said there's this thing called a Laplace transform. It's an integral. Notice it's not a double integral or a triple integral or spherical coordinates or anything crazy like you get into calculus 3 territory. It's really a calculus 1, maybe a calculus 2 type of thing. but the implications of how you use it is really why it's interesting, and we're going to get to that later. But basically, you just stick a function of time in here, you evaluate the integral, evaluate the limits of integration, and if you do it correctly, you should get just a function of s. And we label it capital F of s because capital F and little f are related to one another by this thing we call a transform. We say that that little f yields capital F of s, and later on we'll find out that you can go in the reverse direction and start with a Laplace transform function of s and get the corresponding function of time. So these things are kind of linked by an invisible chain, and that's the chain, which being is the transform. That's why we can take a problem which has functions of time, transform it into the Laplace domain, which is function of s, solve it, usually algebraically, so you don't have to deal with differential equations, you do with algebra, and then you get a function of s. And then we're going to learn how to transform that back to the time domain, and you get your answer in terms of time. And if you do it right, it should be simpler. We also say that the Laplace transform f of s is squiggly L operating on the function of time. And we just talked about improper integral, saying that it's basically like taking the limit, but really what you're doing is plugging in the limits of integration there. And then we do our real problem. So this is how a lot of these problems are going to go. You take your function of time, you put it in, and you simplify. And then you realize the critical step here is that since you're integrating over t, everything here is a constant, right? So I've done the details here. We did the substitution of u, putting it all in there, and pulling this junk out because it's a constant, giving us an integral that everyone watching this should know how to solve, right? So we do that, we plug the limits of integration in. The limits of integration greatly simplify what's happening because this becomes a 0, this becomes a 1, because it's negative infinity. Remember, e to the negative infinity is like 1 over e to the positive infinity, which means 1 over infinity, giving you 0. So all this stuff drops away, giving you negative 1, giving you positive 1 over s minus lambda. So the conclusion block here is the Laplace transform of e to the lambda t is just a function of s. This lambda is locked down with whatever your specific function is. All right, and then as a special case of that, we say, hey, what happens if lambda is 0? Then what you should get if lambda is 0 is 1 over s, right? And if lambda is 0, then the whole thing just goes to 1. So what we're saying is the Laplace transform of the number 1 is 1 over s. If you remember back to Calculus 1, however many years ago that was for you, first thing we talked about, besides limits, but as far as derivatives, the first thing we talked about was how to take simple derivatives, how to take the derivative of a constant. Remember, you had to learn that at one point in the past. How to take the derivative of x, how to take the derivative of x squared. Then you learn how to take derivatives of polynomials. Then you learn how to do it when there's a giant fraction. Then you learn about sines and cosines. You build those skills learning how to take those derivatives. We're doing the same thing with Laplace transforms. We're taking very simple Laplace transforms first, and we're recording these answers, which are useful. Then as we go on, we're going to take more and more complicated Laplace transforms to the point where you can actually get pretty proficient. Then I'm going to show you how to use it to solve a real problem. So right now you look at this and you're like, what's it for? You know, well, I can't get into that until you know a little bit. So just trust me, follow me on to the next lesson. We'll build our skills deriving these essential transforms, and then we'll get a repertoire going so that you have some skills that we can apply to real problems. And whenever you see how much simpler it makes solving certain kinds of differential equations, you'll understand that it's worth its weight in gold just for that application. But also, since differential equations are used in all branches of science and engineering, it really lends the Laplace transform to lots and lots of different situations in real math, science, and engineering. So follow me on to the next lesson in mastering the Laplace transform here in the Laplace transform tutor.